All right. I hope you all are doing well today. Um, we're going to have really a series of three or four brief lectures today on a couple of different topics that are related specifically to Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law. They're kind of, you could call them tricks or tools that you can use that rely on things that we already know in order to both simplify circuits as well as more efficiently analyze circuits. So the first thing that I want to talk about is our source combination techniques. So I'd like to start by talking about how we can combine voltage sources in series, because that's probably the thing that we are most intuitively familiar with. Okay, so I'm going to draw a simple circuit here. Actually, let me annotate this. So here's a simple circuit where we've got, let's say, some 6-volt source like so, connected in series to some arbitrary resistance. So I'm just literally going to call this R. Then over here to the left, let's put another voltage source. Let's make this guy 9 volts. And then over here to the right, I'm going to put a 3-volt source like so. And down here at the bottom, I'm going to close this loop. And ultimately, we are trying to figure out what the equivalent voltage that our resistor sees in this circuit. So this is kind of like what we did in class on Wednesday, except backwards. Before we were trying to use the concept of electrical equivalence to see how we could combine resistors together. Now we're going to use that same concept of electrical equivalence from the perspective of the resistor to see how we can combine all of those voltage sources together. Okay. So if we were to apply Kirchhoff's voltage law around this loop, what we'd wind up getting is negative 6 volts plus VR minus 9 volts plus 3 volts is equal to 0. We could rearrange this and find that the voltage drop across our resistor is just going to be positive 6 volts plus 9 volts minus 3 volts, where I flipped the sign on all of those voltage sources because I moved them to the other side of the equal sign. And putting all of that together, we wind up finding that the voltage source sees a total of 12 volts. So realistically, we could replace this original circuit with the following circuit, where we simply have a 12-volt source, and I'm just going to call this VEQ, is connected to our arbitrary resistance R, where once again, this guy is the voltage drop across our resistor like so. And these two circuits are electrically equivalent to each other. So in short, voltage sources that have the same polarity add together, and voltage sources with opposite polarities, subtract. Okay. So when I'm talking about having the same polarity, in this case, what I'm really meaning is when we applied Kirchhoff's voltage law, we did it in a clockwise direction around this circuit. And so the two voltage sources where we see their negative polarity terminals first, those guys wound up adding together, which we see right here. When we saw the opposite terminal first, which in this case was the positive polarity terminal of the 3-volt source, that guy wound up being subtracted. If we had gone the opposite direction around our circuit, we would have wound up getting the same results because once again, we would have seen that the 9-volt source and the 6-volt source would have had the same polarity because we saw their positive polarity terminals first, and the 3-volt source would have been the opposite polarity because we saw the negative polarity terminal first. So this actually goes a long way in explaining why, if you change the batteries on one of your electronic devices and you put one of them in backwards, it doesn't work. So consider something simple like a remote control, right? Although nowadays, so many of them just have rechargeable rechargeable like lithium ion batteries or something like that. It's getting less and less frequent where you actually have to physically change the batteries out. But when I was a kid, we had to do this all of the time. So usually you would have seen like a diagram inside the battery cavity that looked something akin to this. Okay. So let me just make a simple note here. Here's our battery cavity. Um, and you would have seen usually some piece of metal on this side, and then maybe a spring looking thing on this side, and then a piece of metal on this side, and then that same spring looking thing over here. And for what it's worth, these two guys are usually actually physically connected to each other. So when you put your battery in, you would put it in with the positive polarity terminal over here, and then the negative polarity on that side. And this battery goes in positive polarity terminal on the right, negative polarity terminal on the left, so that when you add those batteries together, your remote control winds up seeing a total of 3 volts. Okay. But if you accidentally put one of those batteries in backwards, let me just put here plus and minus 3 volts. So if you put one of those batteries in backwards, you wound up having, plus 1.5 volts minus 1.5 volts. So you wound up getting a sum total of 0 volts actually being applied across the electronics inside of your remote control. So some of you may have experienced this back in the 120 series if you weren't paying close enough attention and you accidentally put one of your batteries into your battery pack backwards. Instead of seeing the expected 9 volts, you would have actually seen only 6 volts across the terminals of your battery pack, which may or may not be enough to actually power your Arduino and any associated electrical components that you had connected to your breadboard and stuff. Okay. So this is the general rules for connecting voltage sources in series. Before I move along to voltage sources in parallel, does anybody have any questions? I'm not seeing anybody unmuted or anything, so I'm going to assume we're all good to go here. So now let's talk about voltage sources in parallel. Let me scroll up here. Yeah. So I'll get into practical applications of voltage sources in parallel in just a couple of minutes. But suffice it to say, this is something that we don't really think about too often, but we actually do see or experience in our everyday lives fairly regularly. Um, this is also a thing from a circuit analysis perspective that can actually seem a little bit confusing. So I want to kind of explain what's going on here in a lot of detail. Okay. So I want to consider a couple of different cases. Okay. So the first case that I want to consider is something like this. I have, let's say, a 10-volt source connected in parallel to some arbitrary resistance. And over here on the right-hand side, I'm going to have another 10-volt source, like so. I'm going to define the voltage drop across my resistor as positive polarity on top. And what I'm going to do is I'm going to identify a couple of different Kirchhoff's voltage law paths that we should look at. So first, I'm going to do this path right here. And I'm going to write this equation in blue. Okay. So what we would have is negative 10 volts plus VR is equal to 0, which we can very easily algebraically rearrange and find that VR is equal to 10 volts. Okay. Now in green, I'm going to do KVL around this path. So what we would find in this case is negative VR plus 10 volts is equal to 0. And rearranging, once again, we would find that VR is equal to 10 volts. And then lastly, I'm going to do KVL around this outside path. And what we would find is that negative 10 volts plus positive 10 volts is equal to 0. Okay. So this last path doesn't tell us anything about that resistor voltage, but it is something that is inherently true. So negative 10 plus 10 is indeed 0. And then we can see that we get the exact same result for VR over here, regardless of if we do KVL around the left-hand path or the right-hand path. So since they both check out, everything is okay. So when we have a situation like this, everything works out perfectly. All of our circuit analysis rules work. Realistically, we could just replace one of those 10-volt sources with, replace both of those 10-volt sources in parallel with a single 10-volt source, and it wouldn't change literally anything at all about the circuit. But this can very easily break down, okay? So I'm going to draw another circuit here, very similar. Here I've got a 10-volt source. Here's my resistor R. And over here on this side, instead of a 10-volt source, I'm going to put a 9-volt source. Defining my resistor voltage as VR with positive polarity on top, I'm just going to write the exact same KVL equations that I did a moment ago, or at least I'm going to use the same paths. So with my blue path around here, once again, I have negative 10 volts plus VR is equal to 0, which means that VR is equal to 10 volts. Around my green path, like so, I would have negative VR plus 9 volts is equal to 0, which implies that VR is equal to 9 volts. And looks like we have a little bit of a problem because if we do KVL from the left, we get VR is equal to 10. If we do KVL around the right, we get VR is equal to 9. And if we do KVL around the outside, like so, our KVL equation winds up telling us that negative 10 volts plus 9 volts is equal to 0, which is not true. So these things can't be true either because it can't, the voltage drop across the resistor can't be 10 volts and 9 volts simultaneously, okay? So can anybody think of a reason why our circuit analysis here has broken down? Because, just to put this in context, I could very easily build a circuit like this on a breadboard using one of the programmable DC power supplies that we have available over in the IESB in the regular circuits classroom or over in our circuits lab in Nethkin Hall. So if I can build this circuit physically, why does our circuit analysis break down? Anybody have any thoughts? So I don't hear or see anybody volunteering anything, so I guess I'll just go ahead and explain it to you all. Let me make sure that my volume is turned up as well. Oh, goodness. Yeah, I don't have my audio muted, so okay. Anyway, so what's happening here? Fair enough, Joseph, thank you. So what's happening here is effectively because we assume that our wires are short circuits, we are essentially accidentally violating the laws of physics. In a real system, these wires would have some amount of finite resistance, and so this system would actually balance itself out. What we would usually find is that those wires are going to wind up carrying a heck of a lot of current, so much so that we would probably see sparks and they would heat up enough to cause the insulation to melt, but we could actually realize this system. So you really won't see anything like this where you have two voltage sources in parallel that have different voltages in this class from a theoretical perspective, but this is something that you can actually see in real life fairly regularly. Um, so I know that you guys are far too young, probably, to own your own homes and things like that. But perhaps at some point in the past, your parents were investigating potentially using or installing, solar panels or photovoltaics on their roof or something like that. Okay. So that is an example of where you might see voltage sources connected in parallel in real life. And they utilize not only wires with, a pretty decent resistance and a decent amount of insulation, but they also use controllers and things like that to help balance the voltages across each photocell so that they don't wind up starting fires, causing sparks and all of that kind of stuff to happen as well. Okay. Um, for what it's worth, another place where you guys, particularly those of you that go work in the electrical utility industry after you graduate, a place where you might see voltage sources connected in parallel would be battery energy storage systems. So outside of Louisiana Tech, I also do some consulting work for a company called um, Sabre Building Systems by Selection. It's out of Bossier City, Louisiana, and we do designs for lithium ion battery energy storage systems where I wind up trying to plan out how to connect racks containing hundreds, if not thousands, of batteries, um, giving us a total voltage of about 1500 volts per rack. I connect up to 50 of those guys in parallel to be able to drive thousands of amps out into the grid as needed for hospitals. We have an installation at the San Diego Zoo. We have several on islands out in the French Caribbean where they don't have enough infrastructure to have like a traditional electrical utility grid. So if you go into the renewable energy sector, particularly in photovoltaics or battery energy storage, you will see voltage sources connected in parallel literally everywhere. So anyway, I just wanted to provide you guys with a little bit of context about that. So, I'm going to go ahead and move on to how we are going to combine current sources. And we're going to do current sources in the opposite order. So we're going to address current sources in parallel first, and then we're going to wrap up with current sources in series. So I'm going to draw another example here. So let's say that this is a 3 amp current source, direction up. Let's put a 1 amp current source direction down. Here I'm going to have my arbitrary resistance, and I'll define my resistor current. Goodness, sorry about that. Here in a moment. Let's make this guy 2 amps up, like so. And I'm going to arbitrarily say that the current flowing through my resistor is going to have a direction of down, okay? So what we're going to do here is we're going to apply Kirchhoff's current law um, in order to figure out what the total amount of current or the equivalent amount of current the resistor is going to see. So I'm going to apply KCL number 2 at the top node. So just to remind you guys, KCL number 2 is currents entering the node get a positive sign, and currents exiting the node get a minus sign. So the 3 amps is entering the top node, so I would have 3 amps. The 1 amp source is exiting the top node, so I'll have minus 1 amp. IR is exiting the top node, so I'll have minus IR. And lastly, the 2 amps from the source is entering the top node, so I'll have plus 2 amps, and this will be equal to 0. And so what I'm going to do now is simply move that IR over to the other side of the equal sign. So we'll have 3 amps minus 1 amp plus 2 amps is equal to IR. That totally says I5, my apologies. And we wind up getting 3 minus 1 is 2, plus 2 is 4 amps total. Okay. So the equivalent current seen by that resistor is simply 4 amps. So I could, if I were so inclined, replace that whole circuit on the left-hand side with the following electrically equivalent circuit. So to summarize this part, current sources in the same direction add together. So the 3 amp current source was up and the 2 amp current source was up. Those both had positive signs, so we wound up adding them when we combined. And current sources in the opposite direction get subtracted. So does anybody have any questions about how we treat current sources in parallel? Alrighty. So lastly here, we will move on to current sources in series. So this is going to be similar to what we did with voltage sources in parallel, where we can see that with one small change, we will actually break the rules of circuit analysis. This isn't something that's seen particularly often in real life. The only example that I can think of where you see current sources in series is actually specific transistor circuits where the transistors are being used as non-ideal current sources and they are combined in what's called a cascode configuration. So unless you are an electrical engineer and you are going into electronics design or integrated circuit design, you will pretty much never see current sources connected in series, for what it's worth. So let's consider the following circuit where I've got some 3 amp current source connected to some resistor R like so. And then we have another 3 amp current source. And then we've got this bottom bit here short circuited. Okay. So I'm going to define my resistor current IR as flowing through the resistor from left to right. And I'm going to go ahead and also define IR over here on the right hand side for reasons that should be obvious in just a moment. So I'm going to call this node right here the blue node. This node over here to the right will be the green node. And this node on bottom will be the purple node. Okay. And what I'm going to do is I'm going to apply KCL at each of these nodes. And I'm going to use KCL number 1 that says currents flowing into the node must be equal to the currents flowing out of the node. Okay. So KCL number 1 at the blue node says that we have 3 amps flowing in, and that must be equal to the current flowing out, which is labeled as IR. So nothing wild or crazy there. Doing the same formulation of KCL at the green node, we have IR flowing in is equal to 3 amps flowing out. Again, nothing wild or crazy there. And then lastly, at the purple node, using KCL number 1, we have 3 amps flowing in and 3 amps flowing out. So everything checks out. 3 amps is indeed equal to 3 amps, and IR is 3 amps regardless of what node we apply KCL at. So everything works perfectly fine. Realistically, we could get away from this circuit by just saying that the 3 amp source in series with the 3 amp source literally just looks like a 3 amp source. So we could just throw one of them away and it would still be, the circuit would still behave in exactly the same way. Now, if we change the value of one of those current sources so that they're not equal, then obviously things are going to wind up breaking. So if we have 3 amps, our resistor here, then let's put a 2 amp source here and close it off. Once again, dealing with a blue, green, and purple node. I know this is utter overkill because you guys can already see how it's broken. We would wind up having the expressions 3 amps is equal to IR. I guess I should label that IR. My apologies. When we do KCL at the green node, we wind up getting IR is equal to 2 amps. So we have 2 different values for IR, so we know things are broken. But just to make it even more obvious, if we do KCL formulation number 1 at the bottom or purple node, we have 2 amps flowing in and 3 amps flowing out, which obviously 2 is not equal to 3, and these guys don't agree with each other either. So if we ever have a situation where we have 2 current sources that are connected in series and they have different values, we cannot apply our circuit analysis techniques in order to actually solve that system. And I genuinely cannot think of any real world application where we might see something described like this. Okay. All right, so in order for us to get a little bit more practice with this stuff, I'm actually going to work one of your web work problems with you today that's specifically related to not only source combination, but also resistor combination. Okay. So let's work this down here. And I'm just going to put homework 4.5. So this is homework 4, problem 5. I am actually going to turn the circuit over on its side slightly just so that I have enough room to draw it here. But the analysis is going to be exactly the same. Okay. So this is the circuit that we are interested in. And I'm not going to lie, it looks like it can be rather intimidating. Okay. So let's see. I'm just going to use the numbers that were randomly generated for me. So I'm going to call this guy a 21 ohm resistor. This guy over here is going to be a 37 ohm resistor. See. This current source is going to have a value of -3 amps. Um, let's see. This current source right here is going to have a value of 4 amps. I'm going to put a 100 ohm resistor right here. And then down here, I'm going to have, let's see, this guy is going to be 46 ohms. And then we're going to have a 24 ohm resistor. And then lastly, over here, I'm going to have another current source direction down, like so. Let's see, that guy has a value of -6 amps. I forgot this resistor right here. So it's going to be 250 ohms. And we're interested in finding the voltage drop across this current source Vx, as well as the current flowing through the 250 ohm resistor in this direction, which is labeled as Ix. Okay. So this seems like a very intimidating circuit. Okay. The level of difficulty based on the example problems and stuff like that we've worked in this class, this seems like it's going to be much, much harder. And so what I want to do with you guys today is show you how you can use both source combination techniques and resistor combination techniques to simplify this into something that we could have solved a couple of class meetings ago. Okay. So the first thing that I'm going to do is I am going to identify my nodes in this particular circuit. So I'm going to label this first node in orange, and it goes all the way over here, like so. My next node I'm going to do in blue. It's going to be this guy right here. Then in pink, we'll have this guy right here. And lastly, in purple, we'll do this guy. So even though that looks fairly complicated, it's really just 4 nodes. Okay. So since I've identified my nodes in different colors, I talked about this earlier, but I like to use different colors because it lets me very easily see when things are connected in parallel. So for example, I can see that the 21 ohm resistor and the 37 ohm resistor are between the orange node and the blue node. And so that means that since they share both nodes, they must be in parallel. Very similarly, I can see that the 46 ohm resistor and the 24 ohm resistor are shared between the pink node and the purple node. So they must be in parallel as well. So what I can do is I can get rid of the 21 ohm resistor and I can get rid of the 37 ohm resistor, and I'm going to replace them with a single resistor connected between the blue node and the orange node. So that's going to look like 21 in parallel with 37. So I'm putting that in my calculator as 21 times 37 over 21 plus 37. And I wound up getting 777 over 58 ohms. Okay. And because it's placed between the orange node and the blue node, I know I did that correctly. So I'm going to go ahead and kind of erase some of these other little stubs here that might be distracting. I'm going to do something fairly similar for the 46 ohm resistor and the 24 ohm resistor. So I can erase these guys, 46 and 24, and I can replace them with a single resistor connected between pink and purple. So when I put in my calculator 46 times 24 over 46 plus 24, I wound up getting 552 over 35. And once again, I'm just going to erase these little stubs that are sticking out. So now I can see that I have a 777 over 58 ohm resistor in series with a 100 ohm resistor. So I could combine those guys together. And so that would be a single resistance of 6,577 over 58 ohms. And I can combine that 250 in series with that 552 over 35. And that's going to wind up looking like 9,302 over 35. I could combine those resistors together as well, since now they're both between the orange node and the purple node. Let me redo the nodes real quick, just so that it's super obvious. That's technically a different color of orange. There we go. And here's me fixing that light purple. There we go. But I'm going to choose not to combine those two resistors together simply because if I do, I'm going to lose that current IX since it's defined as only flowing through that path that was originally containing the 250 ohm resistor, but now contains that equivalent 9,302 over 35 ohm resistor. So instead of combining my resistors together, I'm going to pivot and combine those current sources together. So I'm going to choose the up direction as my reference for my equivalent current source. So I have -3 up, and then I have, so let's see here. So I'm going to leave that -3 up just so that I don't wind up redrawing that in a second. This -6 down would be the same thing as +6 up. Goodness, I forgot to change the width on this. Like so. So I can combine those two guys together. So -3 up plus 6 up looks like +3. So if I get rid of this guy, this now looks like +3. And now I see that I have +3 up and 4 down. So if I get rid of this guy over here, then that's going to leave what looks like -1 amp in the up direction. And I'm just going to try to erase some of these extra path things here that are getting in the way. So by using resistor combination techniques and current source combination techniques, I've actually gotten this guy down into something pretty easy to analyze. So before I wrap things up with the last couple of steps here, does anybody have any questions about anything that I've done thus far.
Can you re-explain the current addition that you did?
Sure. So let me redraw those guys just really quickly. So over here, it was originally -6 amps down, right? And over here on the left-hand side, it was originally 4 amps down, if I'm remembering correctly. And then this guy in the middle was originally -3 amps up. Okay. So I'll write it out a little bit more instead of just doing it to you. Okay. So I have -3 amps up. I have -6 amps down, and then I also have +4 amps down. Those are all of the different directions and magnitudes of my currents that are connected in parallel. I'm choosing up as my reference direction. So I'm saying that anything that's flowing up is kind of getting a positive sign, and then anything that's flowing down is going to wind up getting a minus sign. So my equivalent current is going to be plus -3 amps minus -6 amps minus +4 amps. So everything that was flowing up got a plus sign. Everything that was flowing down got a minus sign. Does that track, Colin?
Yes, sir, it does.
So when I combine all of those guys together, I get -3 plus 6 minus 4. So -3 plus 6 is +3. -4 becomes -1 amp. And my reference direction was up. So that's why I'm just choosing to replace it with that middle current source. I could have put a current source up on the left-hand side. I could have put a current source up on the right-hand side. They're all in parallel, so it doesn't really matter where it's physically located as long as its direction is indeed up, since I chose that as my reference direction. So from here, how might I go about solving for either Vx or Ix? Actually, I'll tell you from the jump, it's a little bit easier to solve for Vx first, at least in my opinion. So how could I solve for that voltage Vx based on this simplified circuit?
You know the current flowing through the whole system is -1 amp, so can you just do Ohm's law?
Exactly right. That is 100% what I would do. So I would say that Vx is going to be -1 amp multiplied by, and I'm going to use a shorthand notation here, 6577 over 58 ohms in parallel with 9302 over 35 ohms. Um, I'm going to put this in my calculator the real way, but that shorthand notation there with the two parallel lines in the middle just means the resistance on the left is in parallel with the resistance on the right. Okay. So with these big ugly fractions, I just didn't want to wind up writing it all out. And for what it's worth, actually, I believe I'm missing a negative sign. The reason why I'm saying that is because this current is flowing into the negative polarity terminal, so I should put an extra minus sign out front there. So I'll have negative times -1 times, let's see, 65. Wish I had stored this stuff in my calculator, but I didn't have the forethought to do it. 6577 over 58 times 9302 over 35. And all of that is divided by 6577 over 58 plus 9302 over 35, close parentheses. And so if I type this into my calculator correctly, I wound up getting that voltage to be 79.483 and some change volts. Hmm. So when I plug that into WebWork, it just told me that the answer was actually opposite what I wanted. So I got the magnitude right, I got the direction wrong. I'm wondering if when I effectively rotated the circuit by 90 degrees, I might have actually got the currents in the wrong direction or something like that, but the methodology seems correct to me. The current is flowing into the negative polarity terminal, and it should have a value of -1 ohms. So I think I must have just got the directions backward when I redrew it. So my apologies there. Process seems okay. So let's just work with this particular answer for right now. So now that I found that voltage, how would I find that current IX?
The voltage divided by the resistance.
Exactly right. So that would just be Vx over that 9302 angle, or excuse me, not angle, over 35 ohms, which should come out to be 299.067 milliamps. And again, WebWork is telling me that my answer should be these things, but negative. And again, I think it's because I accidentally drew the currents in the wrong direction when I rotated the circuit. So definitely be careful with that as you guys approach it when you do it for your homework, um, sometime this weekend or whatever. All right, so this was an example that was utilizing both resistor combination techniques and current source combination techniques in particular, in order to simplify this rather complicated looking circuit down into something fairly familiar for you all, okay? So unless anybody has any further questions about this particular example problem, I'd like to move on to our second and third topics for today, which are voltage division and current division. So do we need more explanation about source combination, or are we good to go? I will take your silence as we are good to go to move on to other topics. So let's start with voltage division. And so this derivation is going to look incredibly similar to what we did for defining how resistors combine in series until the last couple of steps. Okay. So I'm going to start with a network containing several resistors connected in series that is part of some larger circuit. So here's some resistance R1, some resistance R2, all the way out to some resistance R sub n, like so. I'm going to call the voltage drop across all of these resistors connected in series as V known. because in order for us to apply the voltage division technique, we need to know the total voltage drop across all of our resistors connected in series, okay? I'm going to call this common current flowing through all of our resistors I. We don't actually need to know that. In fact, one of the reasons why we might want to apply the voltage division technique is because it allows us to calculate the voltage across any of these resistors without ever bothering to figure out what that current I is. And then I'm going to label these resistor voltages as V1, V2, and so forth, all the way through V sub n. Okay. So if I apply KVL around this path, what I'll find is that my known voltage, V known, is equal to the sum of the voltage drops across the individual resistors, which I did this in one simple step instead of algebraically rearranging things because this is identical to what we did in class on Wednesday. Just as identical, now I'm going to choose to express all of those resistor voltage drops in terms of that common current I. So that would look like I times R1 plus I times R2 all the way out to I times R sub n. And just like we did in class Wednesday, I'm going to take that common factor of I out of all of those terms, which leaves us with I times the sum of R1 plus R2 all the way out to R sub n. So here's where things get slightly different. Now what I'm going to do is I'm going to solve for that current I. So that would just be dividing both sides by the sum of those resistors. So I wind up getting V known divided by R1 plus R2 all the way out to R sub n. And now I can use Ohm's law to find the value of any of those individual resistor voltage drops. So for example, we could say that V1, which is the voltage drop across resistor R1, is nothing more than I times R1, or V known multiplied by the ratio R1 over R1 plus R2 all the way out to R sub n, like so. And pretty similarly, we could say that V2 is just going to be IR2, or V known times the ratio of R2, sorry that 2 looks so shitty, divided by R1 plus R2 all the way out to R sub n. And so hopefully we all can see the pattern that's happening here. But just in case you don't, I will explicitly spell it out. So we're always going to have V known divided by the sum of all of the resistors in series, and then in our numerator is just going to be whichever resistor that we are interested in. So I could say that in general, the voltage drop across the kth resistor, which is just whatever resistor we're interested in, is simply going to be the known voltage multiplied by R sub k, again, the resistor we're interested in, divided by R1 plus R2 all the way out to R sub n, or in a more succinct form, this is just our known voltage multiplied by the resistor that we're interested in divided by the equivalent series resistance seen by that known voltage. So let's put this into practice with some quick examples. Okay. So let's say that I have the following simple circuit where I've got a 5-volt source. Here, let's say that I have a 10 ohm resistor, an 8 ohm resistor, and down here will be a 7 ohm resistor. And I'm interested in finding this voltage, which I'm going to call V8. And I'm also interested in finding this voltage, which I'm going to call V7. So using my relationship that we just derived, I could say that V8 is just going to be my known voltage. So for this particular circuit, what's the total voltage drop across all of those resistors in series?
Should be 5 volts.
Yeah, it's the only voltage that we know. So it's the 5 volts. Thank you, Colin. Since I'm trying to find the voltage drop across the 8 ohm resistor, that goes in my numerator. And then all of the resistors in series goes in my denominator. So that's going to look like 10 plus 8 plus 7. So that is just 5 times 8 over 25. So 40 over 25, or 8 over 5 if I did my math correctly in my head. Yeah. Now, if we wanted to find that voltage V7, or actually before I find V7, does anybody have any questions about what I did there to solve for V8? I hope it seemed easy because it's supposed to be. So this is a shortcut, essentially, that should allow you to be able to calculate these resistor voltages without having to go through multiple steps, using a combination of Ohm's law, KVL, and all of that kind of good stuff to get the same result. We can now do it directly. Okay, so I hope it seemed easy. If it didn't, by all means, let me know, and I will happily try to explain it to you in a different way or arguably a better way. Well, that's up for, opinion. Okay, so V7. So same basic thing here. Sorry. My known voltage is 5 volts. Because I'm finding the voltage drop across the 7 ohm resistor, that's going to go into my numerator. And then here's going to be all of my resistors in series. So 10 plus 8 plus 7. But I'm now going to put a negative sign out front. And I would like for somebody to try to tell me why they think that negative sign is correct.
Because the current's entering the negative terminal, the 7 ohm resistor.
That's exactly right, Liam. So when we derived this relationship, we saw that our current I was flowing out of the positive polarity terminal of our known voltage and into the positive polarity terminal of all of our resistors connected in series. So in this case, if I labeled my current I, which we never actually bothered to find, as flowing out of the positive polarity terminal, as it flows around the circuit, it does flow into the negative polarity terminal. And so therefore, Ohm's law, and by extension, our voltage division relationship also needs to have a negative sign out front. So thank you for that, Liam. Exactly correct. So now I will have negative 35 over 25, which should be negative 7 over 5. And we've solved for those two voltages without ever bothering to solve for the current directly. Okay. Now, in my opinion, this is fairly handy, but as I've presented it to you right now, it's rather limited in its scope and application because we're not going to have such easy circuits all the time, okay? So what I want to show you now is how we can adapt voltage division to take into account slightly more complicated things, okay? So in yesterday's class, or Wednesday's class, and I definitely don't remember the numbers, so I'm just going to draw something similar. We analyzed a circuit like this. Let's just say here's a 12-volt source. Maybe this was a 15 ohm resistor. Let's make this guy an 8 ohm resistor. This guy down here, a 10 ohm resistor. Actually, let's just make that guy a short. This can be a 20 ohm resistor. And over here will be a 10 ohm resistor. And I believe I asked you guys to find this current, or I might have found this current for you. And when I worked it on Wednesday, I used equivalent resistance. And then also, I think some probably Kirchhoff's voltage law and maybe also Kirchhoff's current law in order to solve for that current IX. I'm going to do that here, but I'm going to use voltage division as my tool of interest to try to eliminate some of those steps, right? So it would be useful to me, I believe, if I could find this voltage, which I'm going to call VY, because I can hopefully see that this current IX that I'm actually interested in is just going to be Vy divided by 20 ohms plus 10 ohms, right? So if I know the voltage between this node and this node, the total voltage drop across the 20 in series with the 10 is whatever that Vy is, and then I divide by that equivalent series resistance of 20 plus 10 is equal to 30, and that gives me the current that I'm interested in. Well, instead of redrawing the circuit a bunch of times and all that kind of stuff like we did on Wednesday, I'm now just going to use voltage division to find that voltage Vy directly, okay? So I can say that Vy is going to be my known voltage of 12 volts. And then in my numerator, I'm going to have effectively the equivalent resistance seen by that Vy. So that would be 8 ohms in parallel with 20 in series with 10. So I'll have 20 ohms plus 10 ohms over 8 ohms plus 20 ohms plus 10 ohms. So I'm treating this equivalent resistance as if it is a single resistor, so that ultimately I have what looks like a voltage source in series with just straight resistors so that I can use that voltage division technique. So down here in my denominator, this would look like 15 ohms plus, and then once again, that equivalent resistance for my numerator. So 8 ohms times 20 ohms plus 10 ohms over 8 ohms plus 20 ohms plus 10 ohms. So Throwing this into my calculator real quick, I'm going to have 12 times 8 times 30 over 8 plus 30 over 15 plus 8 times 30 over 8 plus 30 comes out to be 32/9 of a volt. So for those of you that are still working on homework set number 3, if you look at problem number 4, you can use voltage division to find that voltage V1, and then a second application where you treat V1 as your known voltage to find that voltage V2, and then use that to solve for the current I4 instead of fully collapsing the circuit down to where it's just one small loop and then expanding it to the right over and over again. You can do effectively a double voltage division and then Ohm's law in order to get the results that you're interested in for V1, V2, and I4 very quickly, as opposed to brute forcing it just using specifically KCL, KVL, and Ohm's law. And the method for doing that is very similar to the example problem that I just worked. Okay. Do you guys want or feel the need for any more examples utilizing voltage division, or are you good to move on to current division? And I'm happy to provide more examples if you want them. All right, so let's talk about current division now. So voltage division was a method for us to find the voltage drop across resistors in series. Current division is a method for us to find the current flowing through resistors connected in parallel, okay? So let's start with a network that's going to look incredibly similar to what we did on Wednesday when we were talking about resistors in parallel. So as part of some larger current, there's going to be a larger network. Let's say that I have some resistor R1 in parallel with some resistor R2 in parallel with some resistor R sub n, like so. So let's say in this case that I know the total amount of current that's flowing into that parallel combination of resistors. And because all of those resistors are in parallel, they have the same voltage drop V across them. I'm going to define my resistor currents as I1, I2, and I sub n, like so, where I chose the direction down so that all of the currents are flowing into the positive polarity terminal, so that when I use Ohm's law here in a minute, everything gets a plus sign. And if I apply KCL to this network, particularly currents flowing in is equal to currents flowing out, I wind up getting I known is equal to I1 plus I2 all the way out to I sub n. Using Ohm's law, I can express all of these resistor currents in terms of that voltage V. So that's going to look like V over R1 plus V over R2 all the way out to V over R sub n. And what I'm going to do now is I'm going to solve, actually, I'm going to pull that V out, excuse me, so that I'd have 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. And now I'm going to solve for that voltage V. So V would be simply I known divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. Since I now know what my common voltage is, I can in turn determine any one of those individual resistor currents, okay? So I1 is just going to be V divided by R1, but I'm going to choose to express this slightly differently. I'm going to call this V multiplied by a factor of 1 over R1, so that when I substitute in my relationship for V, it comes out in a form more similar to what we saw for voltage division. So this is going to look like I known multiplied by 1 over R1 divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. Very similarly, if I wanted to solve for I2, that would be V multiplied by 1 over R2, or I known times 1 over R2 divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. So we could say in general, the current flowing through the kth resistor, which is just whatever resistor we're interested in, is simply our known current multiplied by 1 over R sub k divided by, once again, 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. And we can actually simplify this down, and I'll show you what that looks like here in a moment, but I actually prefer this thing right here, okay? The reason why I like this particular representation is because, again, it looks very similar to the voltage division relationship, except we're just using the reciprocals of resistors instead of just the resistor values themselves like we did with voltage division. But anyway, this does simplify down to our known current multiplied by the equivalent resistance of all of our resistors in parallel divided by the resistor that we're interested in. Okay. So this particular formulation of current division works for literally any number of resistive paths that are connected in parallel. Okay. A lot of textbooks only derive this out for exactly 2 resistors in parallel, and I'm going to show you what that looks like, just because in some of my old test solutions, I used that old method, and so I want you to know where it's coming from, okay? But as of the last, 3 or 4 years, really, I only teach current division this way, and I only apply it this way using the reciprocals of the resistors. So if we consider two resistors in parallel, so let's just call this guy I known. Here's R1, and here's R2. Let's call this current here I1, okay? If we use the method that I described above, we would see that I1 is going to be I known times 1 over R1 divided by 1 over R1 plus 1 over R2. Okay. So I can manipulate this very similar to how we defined two resistors in parallel by multiplying this factor of 1 over R1 by R2 over R2 and multiplying this factor of 1 over R2 by R1 over R1. And so that winds up giving me I known times 1 over R1 divided by R1 plus R2 over R1 times R2. Okay. So coming over here, that's the same thing as 1 over R1 multiplied by R1 times R2 over R1 plus R2. And we can see very easily that this R1 cancels that R1, and we're just left with I known times R2 over R1 plus R2. The reason why I really don't like this method, even though it's the one that's taught in practically every circuit analysis textbook, is the thing that's in the numerator is actually the path that we're not interested in. So it looks so different and it's so easy to make mistakes with. I usually don't teach it at all. I'm showing it specifically to you guys, just because it will help you understand some of my solutions from the old tests and stuff like that, where I applied current division, but before I started teaching it in this new, more generalized form. Okay. So if you're comfortable with it, absolutely use it. It is slightly simpler, but it only works for exactly two resistors in parallel. If you're not sure, go back to that fundamental definition that I just underlined in green, where it's using the reciprocals of the resistors, because it's always going to come out correctly and it's applicable for any number of resistors connected in parallel. Okay, so I want to work out a couple of quick examples here, and then that'll be enough for us to call it a day. So let's start with just simple direct application of our current division relationships, right? So let's,
Of our current relationship.
oh my goodness, my phone is spying on me. Sorry about that. Let me tell Siri to leave me alone. So let's say that I have a 5 amp source like so. And let's make this something real simple so that intuitively it'll make sense as well. So let's say that this guy is a 1 ohm resistor. And this guy is a 4 ohm resistor. And I'm interested in finding this current, I1, and for what it's worth, this current, I4. So without applying any math to this whatsoever, can any of you guys tell me what you think either I1 or I4 is supposed to be? So to me, since I1, or excuse me, since 1 ohms is 4 times smaller than 4 ohms, it should carry 4 times as much current. Okay, because we know that current is going to choose the path of least resistance, so it's going to split up, and more current's going to flow through the 1 ohm resistor. And again, because 1 ohms is 4 times smaller than 4 ohms, it should see 4 times as much current. So I believe that I1 is going to come out to be 4 amps, and I4 is going to come out to be, in this case, -1 amp because it's flowing in the wrong direction, but we'll get there in a moment. I just want to bear this out with the math as well, okay? So if we plug in things to our equation, we would have 5 amps times 1 over 1 ohms divided by 1 over 1 ohms plus 1 over 4 ohms. And if we throw this into our calculator or go so far to say 1 over 1 ohms is the same thing as 4 over 4 ohms, we wind up getting 5 amps times 4 over 5 comes out to be exactly as I suggested, 4 amps. Okay. For I4, we would have 5 amps times 1 over 4 ohms divided by 1 over 1 ohm plus 1 over 4 ohms, which is the same thing as going to be 5 amps times 1/5. So that would be 1 amp. But when we defined everything for doing current division, we said that our voltage V had the positive polarity terminal at the head of the known current arrow. So effectively, our current was flowing out of the positive polarity terminal. And in this case, our current I4 is flowing into the negative polarity terminal. So we should get a minus sign. Another way to think about this more intuitively, and it's actually the way that I prefer, would be if we have 5 amps flowing out of this guy, and then it sees 2 paths, we think it should split and flow down through that path, and it should split and flow down through that path. And since it's flowing in the opposite direction as to what we would expect, it needs to have a negative sign. So both ways really come out to be the same thing, but I think the intuitive explanation is probably easier for us to understand with what's going on. So did anybody have any questions about those 2 simple examples? All right. So let's see if we can use current division to figure out how to solve for that current IX from that problem that we dealt with earlier, okay? So let me scroll up here just so that we can wind up getting the same numbers. I might literally just copy the damn thing. So I'm just going to steal this circuit and we're going to reuse it. So we're ultimately interested in finding that current IX, okay? We are now going to find it using current division, okay? Now, you may be saying to yourself right now, Dr. Hartman, you are more of a jackass than usual. There are no known currents in this system. How the hell can we apply current division? And that is a relatively fair assessment, okay? But I think that we should be able to find this current, which I'm going to label as I known, pretty easily just by finding the equivalent resistance of all of those resistors, and then 12 volts divided by that REQ will give us the known current that we could use for our current division relationship, right? So REQ in this case should be 15 ohms plus 8 ohms in parallel with the series combination of 20 ohms and 30 ohms. Or excuse me, series combination of 20 ohms and 10 ohms. Sorry that I misspoke there. So if I throw this into my calculator, I get 15 plus 8 times 30 over 8 plus 30 comes out to be 405 over 19 ohms. And from there, my known current is 12 over that, which comes out to be 76 over 135 amps. So from here, I can use current division and say that the current IX that I'm interested in is my known current, 76 over 135 amps. The total resistance of the path that I'm finding the current through is 1 over 20 ohms plus 10 ohms. So essentially, I'm lumping these two guys together so that it looks like a path in parallel with that 8 ohm resistance. So I'm going to divide that by 1 over 8 ohms plus 1 over 20 ohms plus 10 ohms, like so. And I'm going to throw this into my calculator real quick. So answer times 1 over 30, and then 1 over 8 plus 1 over 30. And I wind up getting a current that is 16 over 135 amps. So does anybody have any questions about this particular example? And if I'm being honest, I'm expecting one in particular. So if nobody asks it, I'm going to answer it any damn way. All right, well, nobody's asking the question that historically practically always gets asked, so I will go ahead and ask it for you. What the hell happened to that 15 ohm resistor? Or a better way of expressing that question would be, why doesn't that 15 ohm resistor show up anywhere in our current division relationship? Would anybody care to venture a guess?
Is it because the current's the same no matter if it goes through it or not?
So I think you phrased that a little bit confusingly, but the gist of the answer is correct. So essentially, we know that all of our known current flows through that 15 ohm resistor, so it doesn't split when it sees that guy. So the current flowing in right there in green is this same current that's flowing out that then splits among those two paths. So if you just have the current flowing, into a resistor that's connected in series, the current doesn't have an opportunity to divide, so it shouldn't show up in your current division relationship. Hopefully that makes sense. All right, I have ranted about circuit topics to you guys for a good 95 minutes straight, so I'm going to stop now. You have 15 minutes left with which to work on your in-class assignments and all that kind of good stuff if you're so inclined. I also understand that it is Friday afternoon, and if you want to dip early, I get it. I'm trying to get out of town to go to Houston to see Metallica this evening anyway, so it's not going to hurt my feelings if we get to leave a little bit early.